This project, called GreenStreaming, is about how to reduce the electricity cost for video streaming systems. We first give a brief background of this project, and then we will show a demo. Internet-scale services like Google Search and YouTube are usually supported by multiple data centers. These data centers consume a huge amount of electricity and thus bring large energy cost to the service providers. For example, in 2010, Google used more than 2 million megawatt hours and was about $140 million. So this scale of energy consumption is equal to that of 200,000 households in the States and nearly 2 million households in China. Service providers like Facebook, Microsoft all have tens of millions of dollars energy costs each year. All of these providers have been beginning to reduce their energy cost. We propose a geographical load balancing or GLB-based approach to reduce the energy cost. This approach is motivated by two observations. First, service providers usually have their data centers geographically distributed in different regions. For example, Google has its data center located in 10 different US states. This figure illustrates 6 major data centers of Google. The second observation is the different dynamics of regional electricity markets. For example, when the electricity price in California is $20 per megawatt hour, the price in Texas may be $30 per megawatt hour. This spatial diversity of electricity price motivates the geographical load balancing. The core idea is to assign more user requests or workloads to data centers with lower electricity price, and turn down or partly turn down the servers in data centers with higher electricity price. Geographical load balancing is useful for many applications. In this demo, we show how to leverage GLB framework to reduce energy cost, using video streaming system as an example. We built a small prototype testbed to demonstrate the effectiveness of GreenStreaming. We used the left 3 machines to emulate 3 data centers in 3 different locations, and use the rightmost one to generate traffic from the clients. So let's go to the demo.
The web page is used to emulate video players, which is viewed by clients. The top video player is for our method, while the bottom one is for an existing method. Our method leverages GLB framework and allocates client requests to data centers in regions with low electricity price while guaranteeing the video quality as much as possible. By contrast, the existing method is a conventional method, which simply carries out load balancing without considering the diversity of electricity price. The window in the right part of the screen shows the real-time electricity price for 3 data centers, which is viewed by the data center operator. The 3 data centers are marked as blue, green, and red. We use the remaining bandwidth of data centers to emulate their loading status. The terminal at bottom right has SSH'd onto the 3 data centers and can change their bandwidth accordingly. We consider 2 cases in this demo. The first case is when some data centers have sufficient remaining bandwidth. The other one is when all data centers are rather overloaded. Let's see the first case. Initially, all data centers are set with sufficient remaining bandwidth. The bandwidth of blue data center is set as 15,000 kilobit per second. The green data center is 10,000 kilobit per second, and the red one is 12,000 kilobit per second. For now, the green data center has the lowest electricity price, and thus our method chooses this data center, while the blue data center has the highest remaining bandwidth, and thus this method chooses the blue data center. Now we increase the load of the green data center by changing its remaining bandwidth to 3,000 kilobits per second. Our method changes to choose the blue data center, which has enough remaining bandwidth for highest video quality and lower electricity price. After we change the green data center's bandwidth back to 10,000 kilobit per second, our method also returns to this data center, not other two data centers, even though the two have higher remaining bandwidth. This observation validates that our method allocates client requests to data centers with sufficient bandwidth and in regions with low electricity price. We now increase the load of the blue data centers by changing its remaining bandwidth to 10,000 kilobits per second. The existing method changes to choose the red data center, which has the highest bandwidth right now. The new window demonstrates the energy cost comparison between our method and the existing method. The red curve is for our method, while the blue curve is for the existing method. From this figure together with the above observation, we can see that, compared to the existing method, our method results in lower energy cost and never gives worse video quality. Now let's move to the second case, when all data centers are rather overloaded. To illustrate this case, we change the three data centers' bandwidth to 3,000, 4,000, and 7,000 kilobits per second, respectively. Both methods choose the red data center, which has the highest remaining bandwidth right now. Their video quality degrades as the figures become unclear. This observation validates that our method also tries to guarantee the video quality as much as possible. Finally, we change all data centers' remaining bandwidth to the initial value. Our method goes back to the data center with the lowest electricity price, the green data center, while the existing method goes back to the data center with the highest remaining bandwidth, the blue data center. To sum up, compared with conventional load balancing method, our method not only gives lower energy cost, but also never has worse video quality. Thanks for watching our demo.